In this video, we're going to go through some identity verification with use of sum and difference identities. So for our first example, we have the sine of alpha plus beta divided by the sine of alpha minus beta is equal to the tangent of alpha plus tangent of beta over the tangent of alpha minus tangent of beta. Now, we are supposed to start with the more complicated looking side. Now, in this case, either of these sides we could work with pretty easily. We could start using sum and difference identities on the left side, or we could start using things like quotient identities on the right side. So what I'd like to do is start with the right side and see if we can turn it into the left side. And over here in purple, I am going to be providing justifications of each step. So for the right-hand side, I am going to do that thing that I said that I was going to do just a moment ago and start using quotient identities. That is the basic strategy where we try to put everything in terms of the sine and the cosine. So tangent of alpha, we're going to refer to that as sine of alpha over the cosine of alpha. And the tangent of beta will be the sine of beta over the cosine of beta. All over. This will be the, once again, sine of alpha over the cosine of alpha minus the sine of beta over the cosine of beta. The justification for this is going to be that we used quotient identities. Now there are two ways that we can proceed from here, which would be to get a lowest common denominator in the numerator and a lowest common denominator in the denominator, or we could simply multiply top and bottom of the big fraction by whatever that lowest common denominator is. I think I'd like to do that. Lowest common denominator in this case is going to be the cosine of alpha times the cosine of beta. Now, these two will distribute through to both fractions in the numerator, and they will both distribute to both fractions in the denominator as well. So our justification, this is simply a step of algebra where we're distributing and doing a lot of canceling. So when we distribute these two to the first fraction, the cosine alphas will cancel out. We'll be left with this sine of alpha and this cosine of beta. Plus. When we distribute to the second fraction, the cosine betas will cancel, and we'll be left with cosine alpha times the sine of beta. When we do that to the denominator, essentially the same algebra will take place. We'll just have a minus sign between them rather than a plus sign in between them. So we'll see sine of alpha, cosine of beta, minus cosine alpha, sine of beta. And in purple, to justify, that was distributive property, and reduce those fractions. You'll notice, however, that the numerator happens to be our sum, or sine of a sum identity. We'll call that sine of alpha plus beta. And the denominator is exactly the sine of a difference identity, which is exactly what we had on the left-hand side. For justification of this step, we will say sum and difference identities. And that completes our proof. Let's try another. Next one I'd like to try out. The cotangent of alpha plus beta is equal to the cotangent of alpha times the cotangent of beta minus 1, all over the cotangent of beta plus the cotangent of alpha. Now with that in mind, I'd like to start this one basically the same way as what we did for the last one. I'm going to start with the right side, and then I will include justifications in purple. Justifications. That's what I keep talking about this this whole quarantining thing, as I tell myself it's just a vacation. Justification. Sorry, as you can tell, slowly descending into madness. Feels good. Feels real good. So, first thing I'm going to do is express everything in terms of sines and cosines, as we frequently do. So we'll call this, let's see, cotangent would be the cosine of alpha over the sine of alpha. Cotangent of beta is going to be the cosine of beta over the sine of beta. Still have minus 1 all over. Cotangent of beta, that will be the cosine of beta over the sine of beta. And let's see, plus the cosine of, oh no, that's supposed to be an alpha. Cosine of alpha over the sine of alpha. To justify that, that would be quotient identities. Now from here, just like on our last example, we have a very, very massive fraction inside of a fraction. I'm going to multiply top and bottom of the big fraction by the lowest common denominator of all of the little fractions. The distributive property says that I'm going to be distributing these over the subtraction in the numerator and over the addition in the denominator. So for the first fraction, we have a sine of alpha, sine of beta in the denominator. We're multiplying by sine of alpha, sine of beta. That'll cancel completely. We'll be left with cosine of alpha times cosine of beta. When we distribute it to the minus 1, nothing will cancel, and it'll simply remain as sine of alpha times sine of beta. In the denominator, when I distribute sine of alpha, sine of beta to the first fraction, the sine of betas will cancel each other out, leaving me with that sine of alpha and that cosine of beta. Plus, when we distribute to the second fraction in the denominator, the sine of alphas will cancel each other out, leaving me with cosine of alpha times the sine of beta. The justification for this step is that that was simply distributing and reducing. So we'll qualify that as algebra this time. A couple of familiar identities pop up at this point. The numerator, cosine of alpha times cosine of beta minus sine of alpha, sine of beta, that's the cosine of alpha plus beta. In the denominator, we have sine of alpha cosine beta plus cosine alpha sine beta. That's the sine of a sum identity. To justify this step, we will say sum identities. And with that in mind, we now have the cosine of an angle divided by the sine of the same angle. Using a quotient identity, that would be the cotangent of said angle. It is a quotient identity. That, of course, is exactly what we had over on the left-hand side, so that completes our proof. I think we have time for one more. And of course, by time for one more, I mean, well, we don't have anything else going on, so yeah, there you go. The cosine of alpha minus beta times the cosine of alpha plus beta is the cosine squared of alpha minus the sine squared of beta. This one is going to be a little bit complicated. Now, given that the right-hand side is already in terms of cosines and sines, I don't really know where I would start with that one. But I do know a start that I could use for the left-hand side. So I'm going to start with the left side. And I'm going to include some justifications in purple. So on the left-hand side, we have the cosine of alpha minus beta times the cosine of alpha plus beta. I would like to apply the cosine of a difference formula and the cosine of a sum formula. Cosine of a difference formula is cosine of alpha, cosine of beta, plus sine alpha, sine beta. The cosine of a sum formula is cosine alpha, cosine beta, minus sine alpha, sine beta. And that was sum and difference identities. At this point, we are going to participate in my second favorite four-letter F word. We are going to FOIL these two guys together. So first will be cosine alpha, cosine beta times cosine alpha, cosine beta. That will be simply cosine squared alpha times cosine squared beta. For the outer term, we are going to have cosine alpha, cosine beta times negative sine alpha, sine beta. That is going to be negative cosine alpha, cosine beta, sine alpha, sine beta. Now for purposes of space, I'm going to move down to the next line right below this. For the inner term, we're going to have sine alpha, sine beta times cosine alpha, cosine beta. So that'll be plus sine alpha, sine beta, cosine alpha, cosine beta. And for the last term, that will be positive sine alpha, sine beta times negative sine alpha, sine beta. So that'll be negative sine squared alpha, sine squared beta. For justification, that was a step of algebra, or we could simply say FOIL. However, for the keen observer, the outer term and the inner term happen to be the same thing, just rearranged in a different order. Given that one's positive and one's negative, if we combine like terms, then they will cancel completely. So we referred to it as FOIL. Turns out it was just a full first and last. Now, this next step is going to be a little bit complicated, and it's going to involve the basic strategy where we keep our eyes on the prize. I see that we now have a lot of squares of trigonometric functions pop up, and when I see squares, I usually think to myself Pythagorean identity. When I take a look at our final answer, eyes on the prize, I should see a cosine squared alpha, which I currently see, and I should see a sine squared beta, which I currently see. You know what I don't see? Is these two guys in the middle, the cosine squared beta and the minus sine squared alpha. So I am going to apply a Pythagorean identity to each of these. Pythagorean identity applied to the cosine squared of beta would be 1 minus the sine squared of beta. Minus, if I apply a Pythagorean identity to the sine squared of alpha, that would be 1 minus the cosine squared of alpha times the sine squared of beta. And again, the justification of this was using a Pythagorean identity. At which point, we're going to do a little bit more algebra. We'll distribute the cosine squared of alpha. So cosine squared of alpha times 1, and then cosine squared alpha times negative sine squared beta. Now for the second set of parentheses, we're actually going to be distributing the negative sign as well as the sine squared of beta. So the 1 will become negative sine squared beta. Then distributing the negative, this will be plus cosine squared alpha sine squared beta. Plus cosine squared alpha sine squared beta. That was a step where we were applying the distributive property, so we'll call that algebra. Please notice now that we have a minus cosine squared alpha sine squared beta and a plus cosine squared alpha sine squared beta. If we combine like terms, this will get us to cosine squared alpha minus sine squared beta, which is our right-hand side. That completes our proof. And to justify that last step, that was combining like terms. So we will refer to it as algebra. Whew, good one.